let's talk about spring graphs. You know, sines and cosines, those pesky things. Okay, so let's imagine you have this spring that's attached to a wall, and the other side's attached to a mass, and at the rest length it's x equals 0, and you pull the thing so that it goes to, let's define this as the negative x direction. So let's say this goes all the way over here, and the mass is at minus a, and then it'll eventually fly back all the way over by energy conservation to x equals a, defined on this side as the positive x-axis. And it'll just oscillate back and forth, harmonic oscillation. And so what's the graph for this? Well, let's turn it like this so we can see this up and down, and imagine we have time going along this axis. I think you can see where I'm going with this, up and down, and if we let time go on, then this up and down is going to look something like this, right? Sorry, I'm a little messed up there then. Okay, so it looks something like that, where this is at x equals 0, and down here we have x equal to minus a, and up here this is x equals a. And you just go up and down, and just for the sake of this problem, let's say that you know that every time it goes up then down, or down then up, it's actually just, this is like 1 second. So this is over here, this is t equals 0, and then when it goes down, it's just a second later. Then it goes back up, and it's t equals 2 seconds. And then over here, this is t equals 3 seconds, and so on. And so now we want to know what function we should use for this graph. Sorry, that's ugly. Let's not look at that. Okay, so what functions do we know? Well, we know sine and cosine, and this one started down here. So this one looks more like a sine. The position doesn't have to be a sine, but let's just choose it to be a sine. So it's a sine of something, and it's a function of time. And so what we don't know is we don't know what's outside of the sine right in front of it, and we don't know what's right here. But we know that it's some oscillating function, and the only one we really know is sine or cosine. So, okay, what would be here and what would be here? Well, we know that sine, no matter what you plug in here, will be between 1 and minus 1. But our function isn't going between 1 and minus 1, it's going between minus a and a. So we can just multiply this times a, and now this function will go between, well, this would be between minus 1 and 1 multiplied by a, so this is just going to go between minus a and a. So it's the amplitude times sine of something times time. So now what's the something? Well, one thing about sine is that you can only put something in here like, you know, some radians or degrees, something that doesn't really have units. It can't have units of seconds or meters. It has to be unitless, whatever you put in here. And there's only really one characteristic time scale in here so that we could cancel out the units of seconds. So basically, whatever we put in here has to be equal to, so this is going to be a sine, and then, so we have time, but then we have to divide it by something else that has units of seconds, so the seconds cancel out. And what would that be? Well, here it has to be the period, because that's the only time thing in a problem like this. And then we could still have some constant here. So now what's that constant? So that constant, and by the way, here the period is, you know, the period is when it goes up then down to the same position, up then down. So the period is just every time it goes up then down then back up. And so the period is going to be this, you know, these are each, like this, each one period. And it looks like that's 2 seconds. So the period is equal to 2 seconds. So, okay, now what is this constant here? Let's just guess it. Let's say it's 1. Okay, so if c equals 1, then we have a sine, so we don't know if this is right, of t over the period. And so that's equal to a times sine of t over 2 seconds. So can that be right? Well, let's see. Let's look at when t equals 1 second. So if when t equals 1 second, that's right over here, and it looks like our function is going to be 0 there. So do we get that? So okay, so t equals 1 second. So it looks like we're going to have sine of 1/2. Well, because t equals 1 second and we have 2 down here. So what's sine of a half? Well, sine of a half is definitely not 0 because sine is only 0 at 0 and pi and 2 pi and 3 pi and 4 pi and whenever you have something times pi in there. And so that doesn't equal pi. So basically what we need is for when t equals 1 second, we actually need this whole thing to be equal to pi, because that's the first time it goes to 0. And so how do we get this whole thing equal to pi when t equals 1 second? Well, we can do that if this is equal to a times sine 2 pi t over the period. So this means when t equals 1 second, we're going to have a 1 up here. We'll have our 2 down here. So that means that we have this 2 canceling with that 2, and we'll have a sine of pi. So this is actually the right expression for the position of our oscillator. And remember that omega is equal to 2 pi over t. So that means that our function is a sine of omega t. So that's where the omega comes from.